Welcome to the next video on simulation of modulation techniques using LabVIEW. So in this video we'll be simulating the standard amplitude modulated signal. So coming up with the equation for the standard amplitude modulated signal, we know that the amplitude modulated signal is given by the amplitude of the carrier times 1 plus the amplitude sensitivity Ka, message signal m of t, into cos 2 pi fct, where fc is the carrier frequency. So this is the equation to go with the standard amplitude modulation. Coming up with the 1 plus magnitude of Ka m of t, if it is less than AC, so it is under modulation where we could exactly recover back our message signal. Coming up with if the magnitude of Ka m of t plus 1, if it is equal to AC perfect modulation, yes, we could recover back our message signal. So in the last case where magnitude of Ka m of t being added with 1, if it is greater than AC, which leads to overmodulation and the recovery of the message signal is not possible. So let us try to keeping these three in mind. Let us try to simulate the amplitude modulated signal and verify comparing with respect to the amplitude of the carrier signal. So we shall switch over to LabVIEW. Yes. So coming over here, I have taken a message signal and a carrier signal. So correspondingly, the message amplitude and the message frequency, carrier amplitude and the carrier frequency. Rest all the components, rest all the parameters, that is the phase, offset, everything is being whatever we have with the default values. So those values itself is considered. Coming up with this message signal m of t have to be added with 1, that is the constant value 1. So what is that I have done is take a adder block, create a constant, and you will have 1 which is being added with the message signal. So this added message signal will be multiplied by the carrier signal. So that is what we have with the equation. The message signal which is being added with 1 have to be multiplied by the carrier signal. So same thing is being implemented over here. Message signal which is added with 1 multiplied by the carrier signal, where we could observe the modulated signal. So coming up with the carrier signal, yes, we could see the carrier signal in this scope. So spectrum of each of the block is being considered by each of the signal is being taken out, where we'll have the FFT block, the peak amplitude of the signal plotted with respect to frequency, which could be seen with the spectrum of message, modulated and the carrier signal respectively. So let me switch on to the front panel. So where we'll have to verify those three conditions which were specified with respect to the message and the carrier signal. So let me give the message frequency around 2000 Hertz and message amplitude let it be 0.5 volt. Coming up with the carrier amplitude, let it be around 3 volt. Carrier frequency, so let me choose the carrier frequency as 30,000 kilohertz. Sorry, 30 kilohertz. So let us run this. Yeah. So I'll just discuss with the waveforms first. Later on, we'll move on to the spectrum. Message waveform with amplitude 0.5 volt, carrier signal with amplitude 3 volts. So coming up with the modulated signal, so where since the amplitude of the message signal being added with 1, since it is less than the value of the carrier amplitude, yes, we have under modulation, where we could look into the envelopes, so that is peaks of the carrier signal. So now let me vary the amplitude of the message signal. Let me keep it at 1 volt. let me keep it at 1 volt. Yes. Yeah. 1 plus the 1 plus 1. So since message amplitude which is 1 volt, 1 plus 1, since it is equal to the carrier amplitude, we could see it has been perfectly modulated, where you could see the phase shift over at this time instant, that is wherever you have zero crossings. Next, if I change this to the amplitude 1.2 volts, if I change it to amplitude 1.2 plus 1, since it is greater than the carrier amplitude, you could see the over modulation portion over here. So that is the envelope which is being protruded over here. So let me still increase the amplitude of the message signal. So check it out, what happens. Yes, which is indicating over modulation. Still increase the amplitude of the message signal. Yes, you could see this over modulation portion, so with the waveform of the modulated signal. So let me increase the carrier frequency so that you could see the envelope very much clearly. Yes, this is the amplitude which is protruded because of the increase in the message amplitude compared to the carrier amplitude. Increase in the message amplitude 1.8 plus 1 compared to the carrier amplitude. So let me go back and reduce. Yes, the over modulation is being removed out. Yes, we have the under modulation, that is which is depending on the amplitude of the message signal and the amplitude of the carrier signal. This is the envelope of your modulated signal. Coming up with the spectrum of the message signal. The message frequency was 2000 Hz. Yes, we have an impulse function. Since a sinusoidal signal, the Fourier transform of a sinusoidal signal is an impulse function, del of f. So I have impulse function exactly at 2000 Hz. So similarly, coming up with the spectrum of the modulated signal, let me just increase the scale over here so that we could observe the spectrum clearly. Coming up with the spectrum of the modulated signal, I have got carrier frequency FC component, which is 39,424, or let me make it exactly 35 kilohertz. Yeah, 35 kilohertz. So frequency component above this carrier frequency is the upper sideband, and this is with the lower sideband. So coming up with the spectrum of your carrier component, yes, an impulse function which is at 35 kilohertz. So let us go study this spectrum with the upper sideband and with the lower sideband over here. I'll just increase or vary the message frequency. Yes, message frequency is being increased. And it is around 3.5 kilohertz. So you could see that compared to 2 kilohertz, so the difference between the upper sideband and the lower sideband is being increased. That is, both the sidebands are moving apart. So which was explained clear. The same explanation was given with DSBSC, but there the carrier component was not present. So over here with the standard AM, yes, we have the carrier component which is with the amplitude 2, so which is with amplitude 2. So reduce this and observe that the upper sidebands and the lower sidebands are coming close to each other. Yes. But there is no variation with the carrier component of the spectrum of the modulated signal. Yes, both are moving apart, and they are coming close to each other. So let me vary the amplitude of the message signal and observe what happens at the spectrum of the modulated signal. Yeah, amplitude is now around 0.5. So over here, which is around 0.5. Increase the amplitude. You could see that the power with the amplitudes with the upper sidebands and the lower sideband is being increased. So increase it further. So make it 1 such a way that so you have perfect modulation. Yes. The power or the amplitude with the sidebands is half the power compared to the carrier component. So let me further increase it. Where you could have over modulation. So looking into the waveforms, yes, you have over modulation over here. So we'll have a look. The amplitude of the sidebands is being increased. Yes, if I still increase it, yes, amplitude of the sidebands is being increased. So with waveforms, it is indicating it is being over modulated. So the same with spectrum of the modulated signal. So to go demodulate, this condition is not possible for the demodulation process. That is, to trace the modulated signal will if we trace the modulated signal, that is the envelopes of the carrier signal or peaks of the carrier signal, will get back our message signal. But if I try to trace back which is an over modulated signal, so we'll have this protruded waveform which will not be exactly as that of your message signal. That is why reduce the amplitude of the message signal. Now if I trace the envelopes or if I trace the peaks of the carrier signal, yes, we could go demodulate. So have a look into the spectrum also. The amplitudes of the sidebands is being reduced. So let me make the sidebands to move far away from each other. To make that, increase the frequency of your message signal. Yes. So this is what we have with the standard amplitude modulation, where we have the message signal, carrier signal, and even the modulated signal. So we have seen the three conditions: the under modulation, perfect modulation, and with the over modulation also. So same, the spectrum over here, the message spectrum, modulated spectrum, and the carrier spectrum. So in the next video, I'll just stop this, go to the block diagram. Yes, message being added with constant 1, so which is being multiplied by your carrier signal gives the modulated signal and their corresponding spectrum. We shall stop at this point. In the next video, we'll look into the other modulation where one of the sideband will be suppressed and the other sideband will be transmitted. Even the carrier signal will be absent in the next coming modulation techniques. Thank you.